Hello guys, welcome back to my channel Gamma Die Gamma. So in the last video, please check it out if you haven't, I discussed Stokes Theorem, and so in this video, just for the sake of continuity, I'm going to discuss the divergence theorem, Gauss's divergence theorem. So let's get started. Okay, so we have with us here a cube. Let's call this point here x0, y0, z0, and then this length here as delta x, this length here as delta z, and the back length there delta y. And you can notice that all of these guys are in the appropriate direction of the axes. So if I draw quick axes here, this will be z, this is x, and that is y. We are in a three-dimensional space here. Okay, so consider some vector function taking points from R3 to R3. Let's consider, since this is a closed surface, the closed surface integral of V on this surface S. So again, notice that we have this area vector dependence for this surface integral. So we need to be careful which faces to take and what is the direction of the area vector. So for the face that's away from us, so this face that's facing us, the face opposite of that, the face that is most behind us, which is most away from us, this face, for that face, our area vector is in the y direction, because an area vector is perpendicular to the plane of the surface, so it's going in the y direction clearly. And for the face that's opposite this green shaded face which is closest to us, it's facing us literally, for that guy the area vector is in the negative y direction. So I want to club both of those faces, because notice that only both of them are in the xz plane. Only this green face and the face opposite to that are in the xz plane. That's important, because then we can set up our double integral with the upper and lower bound x0 plus delta x and z0 plus delta z. For the face that's behind the green shaded part, we have v sub y, because we're dotting them, right? So our vector field v can be expressed as vx, vy, and vz. So if you do a dot product with the vector, the area vector that's pointing in the y direction, and this vector field, you're going to get the y component of the vector field. So vy evaluated for the face that's behind, we have x, y, y0 plus delta y in the y place, and z. We keep x and z as it is because we're integrating over them anyways, and they are the variables of integration. Notice this factor. But that's not quite it. We also have to take into account the first face. So let's just leave some space here. So we have to subtract Vy, the front face. We have a minus because the area vector points in the negative y direction. X, this time we have y naught because it's in the y naught. Y naught value is fixed on this face. Z, and as I suggested before, integration is dz dx. Okay, so this was for these faces, the one in green and the one opposite to that. Now let's consider the other faces too, because we have to do the entire surface. This is a closed surface integral over the entire thing. Okay, so we're basically breaking the surface down. Now let's consider this face, the one on the side, the one that is purely in the YZ plane. So since in the YZ plane, we have y naught plus delta y as one bound, z naught plus delta z as the other bound. And since the area vector now for this red face points in the x direction, in the positive x for the red shaded part, we have v of x, but evaluated at now x naught plus delta x for this right hand shaded red side, yz, since we're integrating over them, minus v sub x, x naught for the face that's opposite to this guy, minus because area vector is in the negative x direction, yz, and then as suggested before, integration over dz and dy. Okay, time to move on to the top and bottom faces. So let's consider the top face. So since it's in the xy plane purely, our limits are from x naught to x naught plus delta x, y naught plus delta y, and vz, because the area vector will be in the z direction, so dot with the vector field v, we have a vz component, and xy, z naught plus delta z, similar to the cases before, minus for the negative area vector vz xy z naught dy dx. Okay, now what do we do? Well, we can do one thing. We can look at these differences in the limit that delta x, delta y, and delta z all tend to 0. Okay, so if we closely observe these differences, let's notice the difference in x first in this limit. Well, you notice that v of x evaluated at x naught plus delta x yz minus v of x at x naught and yz divided by delta x is equal to the partial derivative of v of x with respect to x evaluated at x naught y z. Similarly, the difference in y, vy of x, y naught plus delta y z minus v of y, x, y naught and z divided by delta y is simply equal to the partial derivative of v of y with respect to y evaluated at x, y naught and z. Similarly again, finally, v of z evaluated at x, y, z naught plus delta z minus v of z evaluated at x, y, z naught divided by delta z is simply the partial derivative v of z with respect to z at x, y, z naught. So with these differences, you notice the quantities inside are just the partial derivatives multiplied by these appropriate delta factors. And this only works as long as these guys are small. Otherwise, we would need to approximate this by other terms, second order derivatives too, because this becomes some sort of a Taylor series that way. Okay, so if we plug all of that in, we simply have the closed surface integral over S of the vector field V. This simply becomes integral x naught plus delta x. Actually, my bad. X naught to x naught plus delta x, y naught to y naught plus delta y, of partial vz respect to z delta z dy dx plus integral from y naught to y naught plus delta y, z naught to z naught plus delta z, partial vx with respect to x, delta x dz dy, plus finally we have x naught plus delta x, z naught plus delta z, partial vy with respect to y, delta y dz dx. Okay, so notice as delta y, delta x, delta y, delta z approach 0, this from being a normal cube becomes an infinitesimal cube. So for so this integration, we can plug these partials, although they are themselves functions of x of those variables of integration, each of them, we can plug them out of all the integration just because delta x, delta y, delta z goes to 0. So it becomes a differential cube where the derivative remains the constant. In this case, the partial derivative. So we can plug all of them out and then evaluate the integrals just for dy dx and dz dy and dz dx. So we get all these factors up ahead. So we have the factor of delta y, delta z and delta x for all three terms, and since you can commute multiplication, you can write everything in order. So we have partial vx with respect to x plus partial vy with respect to y plus partial vz with respect to z, but multiplied by this common collective commutative factor of delta x, delta y, delta z. And that is the closed surface integral, which, and if you recognize the quantity inside, this is just the divergence of V times delta x, delta y, delta z. And again, as we did before for Stokes theorem, we can take up any arbitrary, we can take up some arbitrary volume, call it capital V, fill it up with differential cubes, these differential cubes that we initially started with, and we can completely fill them up. Completely fill them up, and notice that just like Stokes theorem again, the contributions of the sides of the cubes that are sort of adjacent to each other, well, those contributions are going to 0 because the area vectors for these consecutive, for this bottom face and this top face and this bottom face, those two area vectors are equal and opposite in magnitude, so they will just cancel off. And this is also true for these sides. So all these all adjacent surfaces will basically get cancelled out until you just remain with the sides that are not touching any other side, the face of a cube that is not touching the face of any other cube, which is just the boundary of the volume V. And a boundary of a volume is just going to be the surface area of whatever figure this was. So putting all of these cubes together, you just get the surface area of this entire thing. So you can call that, say, I don't know, S prime, the closed surface area of this figure, V prime dot dA. And since you integrate them, you place them in this entire volume, this delta x, delta y, delta z will become dx, dy, dz, but in a triple integral over the volume capital V. And we can generally represent this with better notation. You can call this d tau, this differential volume element. And this, friends, boys and girls, women and men of all ages, is Gauss's divergence theorem. And again, this is the part where you're placing all these cubes in this volume, is where the orientability of these surfaces comes into picture. Because if we wouldn't orient them, we would not have a clearly defined area vector, and then the area, since there's no area vector, this notion of like stuff cancelling out, the adjacent contributions cancelling out, wouldn't make sense. In the case of the in the case of Stokes theorem, we had loop contributions going to 0. We had line integral contributions going to 0 because a tangent vector was clearly defined for an orientable line. Here we have orientable surfaces, so the area vector should be clearly defined, which means that we can't integrate over a surface that's sort of like a Mobius strip, for example. I know this is a really bad drawing of Mobius strip, but I hope you see the idea here. In the case of like the Mobius strip, you don't know what's inside, what's outside. It's a geometrically non-orientable surface, so we can't perform the divergence theorem on that. So divergence theorem only works when a surface is closed and has well-defined orientation. I mean, again, if a surface is not closed, it won't enclose any area. So it won't enclose any volume. So this volume integral wouldn't really make sense. Okay, so we're done with our derivation and or proof or whatever. Now let me give you a general overview of what is going on here with 2 dimensions, 3 dimensions, with Stokes theorem and Gauss's theorem. Okay, so we had 2 dimensions. Let's say we had 2 dimensions first. 2 is the least number of dimensions to actually start thinking about multivariable calculus. And for 2 dimensions, we could do this for a loop in 2 dimensions. And we would get Stokes theorem for 2 dimensions, which is called Green's theorem. I didn't do Green's theorem separately because I thought it's a special case of Stokes theorem in 2 dimensions. Okay. So it was for a closed loop. For 3 dimensions, well, we had a loop in, we could have a loop in 3 dimensions as well. Again, a closed loop in 3 dimensions. And we would call it Stokes theorem, and this I proved in the last video. So please check that out if you haven't. We could also have a surface, a closed surface, like we just had one in the derivation of Gauss's theorem, and we would get Gauss's divergence theorem if we had a surface, a closed surface. Okay, so these are like the cases we're concerned with because we are actually working on R3. Notice that this manifold, that's a better word for this. I'm not going into the definition of manifolds, but this construct here, I can't call this is a loop, I can't call this a surface, but this construct here is a sort of one dimensional. It gives you one degree of freedom. You can parameterize this with one variable. So I call it 1 degree freedom, which is also known as, although it's not the right mathematical definition, a 1 manifold of order 1. So a loop is a 1 manifold. A surface is a 2 manifold. Because you can parameterize it with 2 variables, it gives you 2 degrees of freedom. Okay. And then for a 1 dimension, we had a very simple theorem which was called the fundamental theorem of single variable calculus, which said that when you're basically integrating from point A to point B, you basically have to take the antiderivative and then plug in point A from the end point minus plug in the start point. That was the fundamental theorem of calculus. This was basically what a special case of all these things in 1 dimension. And since we are still in 1 dimension, we can only work with 1 manifolds, which was 1 straight line, and the direction was defined because it was single variable calculus back then. And you know what? there's actually a general theorem for n dimensions, any n dimensions. It's called Stokes Theorem. On k manifolds. Now this number k is always less than n, because notice the general pattern going on. We're in 3 dimensions. We can have one manifold, yeah, because that's a loop, right? We can have a 2 manifold, fine, that's a surface, but we can't have a 3 manifold. And if you think about it in that way, remember what divergence theorem was: the closed surface integral over some surface was equal to the volume integral of the divergence of that vector field. If we had a 3 manifold here, we would have the triple closed volume integral of some vector, of some scalar field, or maybe some vector field, maybe orientation would be defined differently, being equal to a 4-dimensional integral of the higher sort of analog of the divergence or the differential operator. And since we were working with R3, our function was taking points from R3 to R3. We can't have something which is a 3-dimensional manifold. We can't integrate over that, a closed integral over that. Similarly, you see the trend, k has to be less than n. So this is what's going on in the most general sense. You can also talk about 0 dimensions, but a 0-dimensional manifold is sort of like just a point, and everything true for a point because it's true vacuously, basically. So this is what is generally going on here. I could also say that, you know, if we were to talk about forms, if instead of vector fields we talked about forms because they're a little more general. This is like the exterior derivative. So if you notice the pattern, we are playing, we're just flirting with some. So if it's a k manifold, we're flirting with a k plus 1 manifold. And its boundary, which by a theorem on manifold is a k manifold. So the general pattern that's going on is we have some differential operator on a k plus 1 manifold. So general thing I could say about that, a differential, more than calling it a differential operator, is exterior derivative of a form, which naturally has order 1 more than the form itself, integrated on k plus 1 manifold. If you don't want to think about exterior derivative of a form, you can call it differential operator of the appropriate vector field is equal to basically the form or the vector field integrated over a k manifold, which is its boundary. So we have this game between the differential operator on a manifold and the boundary of the manifold and the vector field itself. So there's this game going on, this equality of these things, which is a general fact. So this is the most fundamental relationship between these quantities, I think, and this is beautiful. One consequence of all of this, or at least is if we were working on R3, so we just take these two things for now. The most important consequence of this is, assuming you have these equations, you have Gauss's law integral formula, integral form of the Gauss's theorem on Gauss's law, actually, not Gauss's theorem, in electrostatics, which says that if you have a closed surface integral of the electric field across some surface, well, that is equal to the charge enclosed by some body divided by epsilon naught. We can change this by using Gauss's theorem to be equal to a triple volume integral of the divergence of E d tau. You can represent charge as the volume integral of the charge density function. Since the volume is arbitrary, you can set the divergence of E equal to charge density over epsilon naught, and this is the differential form of Gauss's law. We can do this for also for the loop integral, closed loop integral of E or dl, which we know is simply negative d phi over dt, phi magnetic flux. Again, now we can use Stokes theorem, convert this into some surface integral, but we will now have the curl of E dot dA being equal to, we can represent the magnetic flux as again some surface area integral. This is the definition of the magnetic flux, and you get, since the surface area is arbitrary, this differential form. We can again do this for Ampere's law. So you see how useful this is, especially in things like electricity and magnetism, or Maxwell's equations. So we get these nice clean differential forms of Maxwell's equations. Of course, in this term we have this correction factor, 1 over c squared partial E with respect to t, and this is the displacement current term that was put in by Maxwell. I just used Stokes theorem on Ampere's law. Ampere's law did not have that term initially. And again, similarly, if you do that on your magnetic field, for example, if you have some closed surface integral of the magnetic field, that was 0. So triple integral divergence of B d tau was still 0, so divergence of B is 0. So yes, so you see how helpful this was. I hope you really enjoyed this video, and because I think we're done with our discussion of Stokes theorem and divergence theorem, at least for this time in the sequence I'm going in. Please like, share and subscribe to my channel, guys. Recommend my channel to your friends or whatever. It's been fun. I hope you guys are doing well now. I'm going to up my game. I'm going to probably start season 3 soon, officially title it season 3, and see you in another video. Stay tuned. Peace out.